Hello my dear students, welcome to chemistry class, and today's topic we are going to continue is chemical bonding and molecular structure. So in the previous class we were discussing about the formation of covalent bond, ionic bond and coordinate bond, and also some properties of the bond. Is it not, like the bond length, then dipole moment and so on. And today's class we are going to continue with the valence shell electron pair repulsion theory. So that theory is called as VSEPR theory. Okay, I am repeating it again. Valence shell electron pair repulsion theory. So what is the significance of this theory? Okay, now we have studied about the bonds and we have studied about the different type of bonds, and each molecule has its own shape. So this theory gives us an idea about the shape of a molecule. Okay, for example, when you take the water molecule, it is bent shape, bent. Okay, it is bent shape or V shape. Got it? And if you take ammonia molecule, it is pyramidal in shape. You know the shape of a pyramid. So ammonia has that particular structure. So this theory is going to explain us why certain molecules have certain shapes and what is the reason, what is the shape that what shape that has, and what is the reason for that particular shape. And basically the molecule shape is determined by the repulsions. Okay, when there is no repulsion, if there is two bonds and there is no repulsion, then the molecule will be linear in shape. And if you have two bonds, if you have lone pair on it, the repulsion takes place. Got it? So only the lone pair and bond pair is going to determine the shape of the molecule. So based on the repulsion, this is explained. And if you take lone pair, you know, I told you the electrons which are not involved in the bonding are called as lone pair of electrons. So when you suppose to have two lone pairs, then the repulsion is considered to be the strongest. When there is two lone pairs, when the two lone pairs are at the proximity or when they are nearer to each other, then their repulsion is maximum. Okay, and if a lone pair is near to a bond pair, then the repulsion is somewhat moderate. And when two bonding pairs are together, then there is a weakest repulsion. There is no repulsion at all, or no weakest repulsion they have. So this is what you need to understand primarily before getting into this chapter. So lone pair repulsion, that is greater than lone pair bond pair repulsion, and bond pair repulsion is the last one. It is the least thing. Got it? Okay. So based on this, the shape of the molecule varies. See, when you, as I told you, you have two bond pairs. Number of the electron pairs I have shown here. Okay, if the number of electron pairs is 2, that means if you have two bonds, if the two bonds you have, then there is no repulsion and they take a linear shape. An example for these type of molecules are beryllium chloride and mercurous chloride. Got it? And yeah. Now coming to 3. If you have 3 bond pairs, then they take up a shape of trigonal planar. But here you see, I am just giving you only the bond pair idea here. There is no lone pair problem here. All are bond pairs. So if you have two bonds and there is no lone pair, then the shape is linear. This is a table that you need to by heart. Then if you have 3 bond pairs, the shape is trigonal planar, and the best example for this is BF3, boron trifluoride. And what about if you have 4 bond pairs? Then it takes up the tetrahedral shape. An example is methane and ammonium, NH4 plus. It's not ammonia. Ammonia is NH3, and here we have NH4 plus. Got it? Okay. So I'm just, this is different. Okay, ammonia is different and ammonium is different. Now in the case if you have 5 bond pairs, then it is trigonal bipyramidal. Yeah, it's still a pyramid, but it's a bipyramid, a pyramidal shape upwards and downwards. So that shape is called as trigonal bipyramidal, and example for this molecule is phosphorus pentachloride. And in the case if you have 6 bond pairs, the molecule is octahedral in shape. An example for this is SF6. At this point you might be confusing, like you might be totally confused. What are all this? You might feel like I'm speaking in some Greek and Latin. Okay, I'll tell you what are those. And initially you try to understand how the shape varies. After that I'll try to explain you how to find out this number of bond pairs and lone pairs. Now this is a table that's going to show you bond pairs along with the lone pairs. Okay, so initially when I had only 2 bond pairs, the shape was linear. That was the expected geometry. And in case, okay, if it has extra lone pairs, okay, if it has lone pairs along with it, then it becomes a bent shape. For example, you take this one 3. 3 means it can be 2 bond, all can be bond pairs, and 2 can be bond pair with 1 lone pair, and 1 bond pair with 2 lone pair. 3 combinations are possible, is it not? Okay, now you see, when all 3 are bond pairs, when you don't have any lone pair, here I'm showing here. So when you don't have any lone pair, no lone pair, it is trigonal planar. And if you have 1 lone pair, then it is becoming a bent shape. You got it? So we had 2, so I can draw it like this. See, initially it was like this. Okay, if you have 2 bonds, there is some molecule X, or you take it as, you can take it as H2 itself, you can take it, consider here. So you have H, here you have O. Okay, sorry, I'm just drawing a wrong one. Here it should be oxygen and here it should be hydrogen. So I had 2 hydrogens. So how many bond pairs I have here? 2 bonds. Okay, so are you expecting it to be a linear shaped? No, but you have extra lone pair here. Okay, so inside this orbital it has lone pair. So because this lone pair is near to this bond pair is not allowed to stay in 180-degree angle as that happens here. In 2 bond pair it is in 180-degree. But here, because of this lone pair on the oxygen atom, the bond pair of OH is not allowed to stay back in that 180-degree angle position. So it bent. It is becoming, it is repelled away. Got it? It is repelled away and it assumes a bent shape. So this is wrong. This structure is wrong. And what shape it has? Water molecule, what shape it has? It has a bent shaped one. Here, okay, that it has a bent shaped one. So that is what I am trying to explain. Now if you have 4 bond pair, then it is tetrahedral. Out of the 4, if one is lone pair, then it is assuming a pyramidal shape. Got it? From tetrahedral, if all the 4 are bond pair, it is tetrahedral shape. But one bond pair, this is becoming a lone pair. If the molecule has a lone pair instead of one bond pair in that position, then it becomes trigonal pyramidal. Then you see 2 bond pairs with 2 lone pairs. Okay, out of 4, if 2 bond pair and 2 lone pair means it assumes a bent shape again. So 2 bond pair, 1 lone pair is also bent. 2 bond pair with 2 bond pair is lone pair is also bent shaped. Next, coming to 5. So 5 is trigonal bipyramidal. All our bond pairs means trigonal bipyramidal. And if you have out of this 5, if 4 bond pair and 1 lone pair means 4 plus 1. Okay, 4 bond pair and 1 lone pair. So in that case it assumes a Sawhorse projection, or actually this is a seesaw projection. Okay, seesaw shape. You know seesaw, playing seesaw in the parks, children park, you might have seen the seesaws. So that is the shape of this particular molecule. Then if it is 3 bond pair and 2 lone pair, it is T-shaped. Then if it is 3 plus 2 bond pair and all the other 3 are lone pair means, yeah, it is also linear only. So out of 6, if all are bond pair, it is octahedral. So if you have 5 plus 1, 5 bond pair and 1 lone pair, then it is square pyramidal. If it is 4 plus 2, okay, 4 bond pair and 2 lone pair, it is square planar. If it is 3 bond pair and 3 lone pair, means it is T-shaped. Last one is linear. So you see this last column. If you have 2 bond pair and if you have enough number of lone pairs, like if you have 2 bond pair and it is linear. If you have 2 bond pair and 1 lone pair, it is bent. If you have 2 bond pair and 2 lone pair, it is also bent. But if you have 2 bond pair and 3 lone pair, that lone pair it is linear. Though you have lone pair here, it is linear. Why? Because there is a balancing of the repulsions. See, all 3 are in the like 120-degree angle. Okay, and that is actually this lone pair is repelling this bond pair here, but this lone pair is again repelling the bond pair in the opposite side. So that repulsion is balanced, and you're getting that in the linear position itself. That is a proper balancing of the repulsive forces. In the opposite sides, if you have the lone pairs, they mutually push the bond pairs in the opposite sides. So when the push is in the opposite sides, then the repulsion is balanced, and thereby it can stay only in the linear shape. That's the reason. See, here also you have 2 bond pair and you have 4 lone pair. So 4 lone pair means 2 lone pair this side and 2 lone pair other side. So that is balanced. That is balanced, and it is assuming a linear shape again. So that's the reason for all this. So this table is very important. 2 bond pair means linear, 2 plus 1 is bent, 3 bond pair is trigonal planar, 3 plus 1 is pyramidal, 4 is tetrahedral, 4 plus 1 is Caesar, 4 plus 2 is square planar, 5 is trigonal bipyramidal, and 5 plus 1 is distorted trigonal bipyramidal or square pyramidal, and 6 is octahedral. Okay, so I need you all to remember all this. So you can see here, this is another table to show it. 2 bond pair and 1 lone pair. It is bent. So 3 plus 1, it is trigonal pyramidal. It's not bipyramidal, trigonal pyramidal. Then 2 bond pair and 2 lone pair, bent shape. 4 bond pair and 1 lone pair, Caesar shape. 3 plus 2 is T-shaped. 5 plus 1 is square pyramidal. 6 is octahedral. But 5 plus 1 is square pyramidal. 5 bond pair and 1 lone pair. Then 4 plus 2 is square planar. So this is also again one more table that gives you more information about the shapes. Okay, now I say 2 bond pair, 1 lone pair, 2, 3, so many Greek and Latin things I'm saying. But you might be wondering, but ma'am, how do I know how many bond pairs a molecule have and how many lone pairs a molecule have? This is the $1 million question running in your minds right now. Am I right? So I am going to tell you a trick to find out this bond pairs and lone pairs. So for that, what you need to understand is, see, I have given you a table. Okay, in this table I have given you the valence electrons. Till oxygen only I have given you. You can learn more atoms so that you can know, you can solve more examples. Okay, now coming to this. So this table is very, very important. This table only, if you know this, you can calculate the bond pairs and the lone pairs, and you can come out with the value. Well, hydrogen, how many lone pairs, how many electrons, valence number of electrons it has? Yes, of course it has 1. And what about helium? Helium has 2. Lithium again 1. Okay, though the atomic number is 3, the valence electron means the outermost electron, that you know. The outermost electron that is going to take part in the bonding is only 1. And what about beryllium? 2. So boron 3. Carbon 4. What is the atomic number for carbon? It is 6. But only the outermost 4 electrons are going to take part in the bonding. Nitrogen is 5 and oxygen is 6. This should be in your mind. Okay, then we can solve some problems. Okay, now so I have given you some examples also here, like water, like water, ammonia, methane and carbon dioxide. Shall we start with water? Okay, so water means what? H, 2, O. How many hydrogens it has? 2 hydrogens. And go to this valence number of electrons for hydrogen is 1. So 1 into 2. I have totally 2 valence electrons from hydrogen. And how many valence electrons for oxygen? It is 6. So what is the total number of valence electrons? It is 8. So see the second rule. If the total number is 8, you have to divide it by if it is more than 8. If it is more than 8, you have to divide it by 8. If it is 8 or less, then you have to divide it by 2. Okay. So if the total number is more than 8, divided by 8. If the total number is 8, you have to divide it by 8. Or if the total number is more than 8, you have to divide it by 8. So in this case, our total number is 8. So 8 by 2 is 4. What is 8 by 2? 8 by 2 is 4. So in H2O, how many bond pairs it has? Can you say, are there 4 bond pairs? For 4 bond pairs, for making 4 bonds, at least you need 5 atoms. Am I right? But how many atoms we have here? We have only 3 atoms here. Okay? We have only 3 atoms. So out of this 4, only 2 bond pairs are possible. Yes or no? Yeah. So the remaining must be lone pairs. 2 bond pair and 2 lone pairs. Sometimes you have to think logically like this. Some molecules you will have enough, like this number will give you the total thing. So no need to worry. So what in the water case? Water case we got 4. But though we don't have 4 bonds. Because if you want to have 4 bonds, at least you need 5 atoms. Am I right? Like CH4. In CH4, how many atoms in total? 5 atoms. But in water, you have only 3 atoms. So only 2 bond pairs are possible. So 2 bond pairs means the remaining will be lone pair. So 2 bond pair and 2 lone pair. Now tell me the shape. Yes, it is bent or V-shaped. Okay, water molecule has a bent shape or V-shape. Okay, next example. Let's try ammonia, NH3. So for nitrogen, how many valence electron? 5. So for hydrogen, how many hydrogens I have? 3. So 5 plus 3 is equal to 8. 8 again. So 8 by 2. If it is 8 or less than 8, you have to divide it by 2. So again I am getting 4 only here. But how many atoms I have for ammonia? 4 atoms. So out of 4 atoms, how many bonds I can make? I can make 3 bonds. So I have 3 bond pairs and 1 lone pair. Now tell me the shape. Yes, the shape of ammonia is pyramidal. Got it? Okay, next coming to the methane example. CH4. So what is the valence electrons for carbon? Carbon is 4. 4 plus how many hydrogens? 4. So this is also 8. 8 by 2. So totally 4. This is also 4. But how many atoms you have here? 5 atoms. So 4 bond pairs possible or not? Yes, possible. So 4 bond pairs means the shape is going to be tetrahedral. The symbol for tetrahedral is TH. That's why I am writing TH. So the last example, shall we try? Carbon dioxide, shall we try? So carbon is 4 and oxygen 6. 6 2s are 12. 12 plus 4 is 16. Okay, so 16 by 2 is 8. See, we have only 3 atoms, so only 2 bond pairs are possible. So 2 bond pairs, and all are remaining are 2 bond pairs and remaining is 4 electrons, is it not? For one bond pair you need 2 electrons. So 2 bond pair means 4 electrons get utilized. The remaining is 4. So 4 means 2 lone pair again. 2 bond pair and 2 lone pair. So in that case it becomes a linear shaped one. Got it? So this is how you have to find out the shape of the molecules. And in the exam also you will be given molecules and you may have to find out the shape. So for finding out the shape you need to know the valence number of electrons, and this is a super trick to find out the shape of any molecule, provided you know this table. Yeah, you know this table. In that once if you initially it might be tough for you, but if you solve few examples, at least 10 or 15 examples if you solve on your own and you interpret it with the table, then automatically the idea comes into your mind and easily you can predict the shape of the molecules. Any molecule you can predict. Okay. The next concept is the orbital overlap concept. Okay, so first we have predicted the shape of the molecules, and next coming to the hybridization. Before getting into the hybridization, we must know the overlap of orbitals. So how do they overlap, and how, you know, 2 types of bonds are formed, sigma bond and pi bonds are formed. So the question is how sigma bonds are formed and how pi bonds are formed through the overlap of the orbitals. Okay. So what is the shape of the s orbital? The shape of the s orbital is spherical. When 2 s orbitals they overlap like this, it is called SS overlap. When one s orbital overlaps with a p orbital, what is the shape of the p orbital? It is dumbbell shape. So if a linear overlap takes place between them, then you will get a sp overlap. If 2 p orbitals overlap linearly like this, then it is p to p overlap. So SS overlap is there, sp overlap is there, and pp overlap is there. In all these cases, if the overlap occurs like this, then you will get sigma bonds. Okay. Next, sigma bond. This p orbital can overlap in 2 fashions. It can overlap linearly. This type of overlap, what we have discussed, is called as the head-to-head overlap. Okay, head-to-head overlap. And this type of overlap, in here you can see. So this is actually head-to-head and tail-to-tail. This is only head-to-head overlap. But here it can overlap like this also, like sideways. Parallelly it can overlap like this. So once if the p orbital overlap parallelly like this, then you get a pi orbital. Okay, this is pi orbital, and in all other cases linear overlap you get the sigma bond. Okay, sigma bond and pi bond, we say they are formed because of this kind of overlaps. So this is a very important concept that you have to know, so that we can get into the like hybridization in a more detailed way. Okay. Now hybridization, how many types of hybridization are there? So you know, sp hybridization is there, sp2 is there, sp3 is there, then sp3d is there, sp3d2 is there, and so many types we have. But in this chapter we are going to learn this hybridization, sp, sp2 and sp3. So what is the hybridization? One s orbital and one p orbital, they are going to mix, and they are going to give us a shape. In VSEPR theory, what we were discussing, each molecule has its own shape, is it not? Though we have different type of orbitals, that they have a different shape. So they say based on the lone pair they are predicting the shape. But how um, in the terms of orbital concept, hybridization theory is going to explain us why do they get that shape. Okay, because in each atom you have s orbitals, you have p orbitals. Sometimes you have s orbital as the valence electron, sometimes we have p orbital as the valence electron. So even in H2O you take, hydrogen has only one s orbital and oxygen has what? It has only p orbital. So how that s and p are going to mix up and they form that shape. Okay, that is going to be explained by your hybridization theory. So s orbital and p orbital are combining. How you are getting one particular shape? Because s is spherical and p is dumbbell. When they mix up with each other, you should get that kind of shape, but you are getting a linear shaped orbital. How that is happening? That is what is called as hybridization. What is a hybridization means? Hybridization means when you have when you are mixing up two different things, okay, and they become one. For example, you have a red rose and you have a white rose. If you mix those two, if you try to hybrid those two stems, then you will get a pink colored rose, a rose that has the properties of both your red and the white parental rose. That is called as hybridization. Here also s orbital is a different shaped orbital, p orbital is a different shaped orbital. S has a different energy, p has a different energy, but once if they mix up, they are going to produce new orbitals called as the hybrid orbitals. That orbital will not differ in shape. That is a one orbital which has one particular shape and one particular energy. That is why they are giving you a final shape of the molecule is given to you. So one S and one P is mixing up here, okay, and you are getting a orbital like this. After one S and one P mix up like this, what is the final shape of the orbital you are getting? You are getting two lobes, you see. Like this you are getting one particular orbital you are getting, and that orbitals are aligned in a linear fashion at 180-degree angle. That is why the shape is linear. So this is giving us more clarity, no, than the valential electron pair repulsion theory. Valential electron pair repulsion theory predicts the shape of molecules 90%, but it still has some disadvantages. So this hybridization theory gives more insight into this concept. Now when you take, these are some examples, okay. Next, coming to the BF3. In BF3, boron, 1s2, 2s2, 2p1. Boron has actually p orbital. Okay, fluorine has actually f orbital. Both are p orbital only. Both are p orbital, and 3 p orbitals of fluorine and 1 p orbital of boron are going to combine. Okay, 3 p orbitals of fluorine. 3 p orbitals of fluorine and 1 p orbital of boron is going to combine, and after combining, they are going to produce one particular orbital, that is trigonal planar in shape. Okay, that is why the shape is trigonal planar. Okay, this is different. And carbon also you take. In carbon, you have carbon 1s2, 2s2, 2p2. So carbon has p orbitals. Okay, carbon has p orbital, and hydrogen has s orbital. So the p orbital of carbon and 4 s orbitals of hydrogen are going to combine and form sp3 hybridization with a shape of tetrahedral shape. So this is the reason that CH4 is tetrahedral in nature. So again one table that gives us an idea about the angle. So sp hybridization usually has 180-degree angle, sp2 means 120-degree angle, or you can say linear orbital, linear shape means 180-degree, and 120-degree angle for trigonal planar. And what for this one, tetrahedral shape, it is 109-degree. Okay, then 109.5-degree angle, and in the trigonal bipyramidal, that lobes thing is angle is 120 degree, and in octahedral all are 90 degree. Got it? Okay. So well, next coming to the hybridization of carbon. So we are going to, we now you know what is hybridization. Hybridization means the mixing up. So you have sp2 hybridization we have, then sp3 also we have. So in the next class I will be discussing about the hybridization concept in detail.